which talks a little bit about TS as a background information, but more importantly about conductors. Maybe a little bit about the TS conductor first. We are a public benefit corporation, by the way. Not many companies in the U.S. has that designation, and we care deeply about climate change. We have a public benefit focus in sustainable development and greenhouse gas emission reduction, and we take that mission very seriously. We have been very blessed with support from utilities like National Grid and NextEra. They are part owners in TS. In addition to Bill Gates' Breakthrough Energy Venture, they helped us to build the first conductor manufacturing plant in the U.S. We are probably the only conductor manufacturer in the U.S. west of Mississippi, by the way, and it's true. We also have expansion plans that are being seriously taken for the East Coast. We should have major capacity expansions available late 2025 as well. When you look at TS, what is unique, what is different, I'll elaborate a little bit more on that. There are two areas that are really different. One is in the material science aspect. We do feature the best material science has to offer today. And when you think about the conductors, which I will elaborate a little bit more, we're still reliant on century-old technology, by the way. Not just in the US, but worldwide. That's not going to help us to solve the problems that are in front of us. So on the material science side, we do feature the best material science has to offer, and we also feature something that's very important. The protection, effective protection of the strength member in the conductor, which was missing in all the prior generation advanced conductors in the past. With that protection, we also make our technology compatible with traditional work practice. That is actually quite essential in our industry because the linemen in the field has a critical voice. And when you look at the performance with the TS type of technology, you can potentially triple the line capacity. We'll get to that a little bit more. At the same time, reduce line loss by as much as half. A solution will not be embraced if you are not competitive. We can also drive for what we call green discount in terms of project cost savings. That is, when you compare TS solution versus traditional approach on a project capex basis, whether you do reconductoring or whether you do new transmission lines, we offer a very compelling value proposition in terms of a lower project cost. And there's also something that I think as society, including policymakers and the regulators, we should be able to do more in terms of leveraging advanced technology to pay for the necessary upgrade. For example, when you have substantial line loss reduction, there is economic monetary values. Right now, we do not have a mechanism to monetize that and to leverage it effectively to subsidize the cost related to grid upgrade. And we should look into that. When you are able to do that, you actually have a green discount because the line loss saving is available to you every hour, every day, every week, every month, every year. And lastly, I'm also going to talk about smart conductors. Everything else in society is becoming smart. Why shouldn't the conductors? And there's value in deploying smart conductors as well. A little bit about material science and looking at what is incorporated in a conductor. When you look back in the past 100 years, our industry, the evolutions in conductor is actually a story about material science. The evolution of newer materials that made it possible to have newer class of conductors available for our industry. Back in 1908, when ACSR conductor was developed, which is the yellow row, we had high-strength steel at the time. But the high-strength steel 100 years ago is not quite strong enough. So what we had to do is we had to leverage the very high strengths in the hard aluminum. Now, when you use hard aluminum, you do have some handicaps. One of the major handicaps is it is not the most conductive type of aluminum, and the other one is it's got a temperature limit. The reason for that is hard aluminum starts to lose strength at the temperature about 93 degrees centigrade because it's going to anneal, become soft, and you're going to lose strength permanently. You're going to have a sag issue as a consequence. And when you use steel as a strength member, there's some more sagging, they're heavy, and it's vulnerable to corrosion as well. So it is not really an ideal solution, but nevertheless, it's been around for the past 100 years. The aluminum industry in the past 100 years has been more or less focused on the strength column here. How do we get even higher strength out of aluminum, or maintaining high strength at high temperature? But when you look at the electrical properties of these different types of aluminum, we trade away electrical conductivity for that mechanical strength, which is the wrong trade-off when you are building a conductor. Because the purpose of a conductor is to move electrons, and you want to do that efficiently. The better aluminum is actually the so-called annealed aluminum. These are high purity annealed aluminum that has the highest electrical conductivity. It also supports high temperature as well when you need that additional capacity in the conductor. Provided, though, we can address the lack of strength in the annealed aluminum. So now we go to the right side, which is really about the strength members in terms of building a conductor. About 50 years ago, the steel industry was able to come up with stronger steel, or maintaining high strength at high temperature. These are so-called mixed metals. Now you have stronger steel, which can facilitate the integration of the annealed aluminum. Now you have a conductor that can go to high temperatures when you need it to for that additional capacity. And this is how ACSS is developed, and that's also where ACSS is typically used, which is reconductoring, to get that additional capacity. However, when you use ACSS, you do have to deal with the compromised solar sagging in particular. Why? Because we're still featuring steel in the strength member, and the steel material is still heavy, and they have very high solar expansion. So what does solar expansion got to do with the conductor? Well, when the lines run hot, the stretching of the steel makes the conductor longer, and that results in sagging. And that sag is actually substantially more than the baseline conductor, which is typically ACSR. So what it means is, if you're doing reconductoring, you have to deal with the excessive sag. That means you have to raise the tower height to manage clearance. That adds significant cost as well as time to the projects. If you do new lines, by the way, and some utilities do use ACSS conductor for building new lines, you have to manage the excessive sag as well. The way you do that is typically you will be reducing the span distance between the towers. So you will be ending up developing or building a transmission line with more towers. That adds up significant cost to your project capex. And to address that issue in terms of heavy core and highly, somally sagging core, we have, I'm going to skip EMR here because we don't use EMRs in the US. The EMR story here, they have a very low solar expansion, but they have very lousy strength, so they had to combine with one of these high temperature aluminum alloys, makes them very lossy. And they also are magnetic in terms of steel properties. So what it means is they've got a huge surge impedance. They cannot go very far, and you have to use a lot of capacitors to compensate for the inductive impedance. And by the way, invars are very expensive if you do have to consider invar. Going back to the strength member side, to address the weight and also the thermal expansion, composite core was developed about 20 to 30 years ago to substitute for steel in terms of newer generation conductors. I'm going to talk about two types of them. One is called ACSR, which is a ceramic fiber, aluminum oxide, in an aluminum matrix. And this particular composite core, it did reduce thermal expansion of the thermal sag by half, and reduce the weight by about half as well. And that allows you to manage the what we call thermal sagging. The challenge though is when you use ceramic fiber, there's a very limiting tensile stretching. Or just put it in numbers. These type of ceramic fiber, in theory, you can only stretch to about 0.7%. And to put it in perspective, carbon fiber, you can normally stretch to 3 times that, about 2.2%. And by the way, if you do steel, it is about 3.5%. So what that means is the composite core out of the ceramic oxide is actually quite low. It's actually no better than the century-old high-strength steel at the time that ACSR was developed. So ACSR conductor has to be combined with one of these high-temperature aluminum alloys, which doesn't give you the best electrical. And the other issue related to this limited stretching is it is a very delicate material that you have to manage your bend angles, the sheave wheels, the conductor reels very carefully. Because if you have excessive bending, you will be snapping the composite material. And that is a very bad situation to be in. And the material is also very expensive. We're talking about ceramic fiber about 10 times the cost of carbon fiber typically. And if you compare it to aluminum steel, there's no comparison. The other type of composite core conductor is using glass carbon hybrid core, and I use the generic terminology called CFCC, carbon fiber composite core conductor. This composite core, which is combining glass fiber and carbon together with epoxy matrix typically for that high temperature capability, you do have a high strength out of the core. You do reduce the thermal expansion further, and it's a pretty low density material as well. So in a way, it's actually quite ideal. Now you are able to combine this material with the best possible aluminum for building a conductor. That's the annealed aluminum for pretty decent electrical performance. The challenge though is when you use substantial amount of glass in the composite, you actually rub down the properties that are possible with a carbon fiber composite. One of the major compromises is the modulus of the conductor is actually very low. What does it mean when the modulus is low? If you have heavy ice, in the northern part of US, or you don't have to go to Alaska, by the way. You're gonna, even in Chicago, you got to deal with inch thick ice for designs in terms of managing sag. You have to address the sagging associated with weight. The weight could be from ice building on the conductor or strong wind blowing at the conductor if you're in the coastal area, or when you have a long span, the weight of the conductor itself could drive significant sagging as well. And this really put this conductor in a compromised situation. The other challenges are these type of composite core with the carbon fiber and the glass fiber being parallel to the axial direction, which is normally called unidirectional composite, they're exceptional in the fiber dominated property like strengths. But when you compress on them from the ends, or when you bend it, the compressive strength is actually lousy because compressive strength is dominated by the matrix, organic matrix material. It's only about 60 to 70% of the tensile property. So what it means is you will always prematurely fail on the compression side when you bend it. So you have a compromise situation where if you don't manage the bending angles or the bending radius properly, if you have a sharp edge situation like the table edge here, you bend it, it's going to snap. That has been one of the Achilles heel in that type of product. The other challenges for this type of product is the composite core is naked to the environment. What do I mean by naked? We strand the aluminum strands directly onto this glass carbon hybrid core, and all of those interstitial gaps, it allows moisture to go in there, it allows the oxygen to go in there, and God forbid if you have a bird cage, okay, you're going to have UV ozone from corona directly affecting the polymer matrix. The fibers are okay. It is the polymer matrix that are holding the fiber together that are getting compromised when you have the strength member directly exposed to the environment. For example, moisture. Moisture is the polar molecule, and it does go into the organic matrix, it breaks the organic bond, and it makes the material even more vulnerable to compression failure, and it's also going to drive down the so-called glass transition temperature, which is what limits your high temperature performance. And when you have oxygen, because these conductors are expected to operate at high temperature, you are mixing organics, high temperature, and oxygen together. That's a bad recipe when you talk about longevities. So those issues have to be addressed as well. And lastly, we traditionally do conductor splicing by inserting the strength member like steel wires inside the steel tube, crimp on them, and then slide over the aluminum sleeve or aluminum tube and crimp the aluminum tube onto the conductor directly. That's how you have the mechanical load pass as well as the electrical load pass. You cannot do that with the glass carbon hybrid core, because if you insert the composite core directly inside the steel tube and then you crimp on that, you're going to crush the core. So you have to come up with new ways, new fittings to do splicing, to do dead endings. That require training of the line crew, and actually the line crew have to be certified to do the work. Imagine if you have a weather emergency, you have to do restorations, you have to look for these certified line crew to do the work. That won't be a good situation to be in. But back to material science. If you have a carbon composite that does not have glass fiber in it, you have some of the dream properties in terms of developing a conductor. For example, the weight, the density of the carbon composite, it is only 20% of the weight of steel. If you look at the thermal expansion, it's virtually non-existent. Why? Because carbon fiber is one of the two materials that is known that actually shrinks when the temperature goes up. The other material is actually water. When the water converts from ice to liquid water, there's actually a warning shrinkage. These are the only known material that has this phenomena. And you have a strength for the carbon composite that's twice that of steel, and you've got a very respectful modulus that allows you to adequately manage sagging from ice load, wind blowout, long span as well. What we do in TS is we combine the best in the strength member side, which is the carbon composite, and the best from the aluminum, that's the inert aluminum. That's how we develop TS. And you may say that you are having the best DMA, quote unquote, in the material combination, but that is no guarantee that you have a great conductor. The issues that we talked about associated with the other type of advanced conductor, we have to address them. Especially the protection against bending failure, the protection for the vulnerable organic constituent in the conductor, and compatibility with traditional work practice. These are things that we have to address. And these are done by this aluminum encapsulation protection. We basically take a small amount of these conductive aluminum for dual purpose. They're still conductive, but we also use it to protect the carbon composite core. That is actually essential for the conductor to perform. The first part of the protection is we actually pre-stretch the carbon core in our manufacturing process, and then we introduce this aluminum encapsulation layer. By the way, it is relatively thick, because if it's too thin, it won't work. What we're trying to do is we're preserving that pre-stretching in the carbon core, in the TS conductor, in the encapsulated core. And why do we do that? We mentioned about unidirectional composite has this limiting, compressive strength from the ends or from bending. Now, if we can preserve pre-tension in the carbon core, imagine if you have the conductor bended. It does not automatically create compressive stress from bending, because you have to overcome the pre-existing tension before the material go into compression, which is the vulnerability that these type of material had. So now you have a situation where you no longer have that compression vulnerability. We have a much better ability to handle, sharp edge bending or small radius or angle changes in the field. That is the necessary robustness you need in terms of working with conductors. The other part in terms of the protection is we're shielding the composite core, especially the vulnerable organic constituent for life from environments like moisture, like oxygen, like UVs or ozone. They will never have the chance to go in to affect the composite core or the vulnerable organic constituent. And that's how that protection for longevity comes in. And lastly, this aluminum layer that's around the carbon core, it acts as a cushion. So we can actually directly insert the encapsulated core into the steel tube that the line crews are all familiar with doing splicing for ACSR or ACSS conductors. You can use the same tool, same equipment, same methodology, same training to do the conductor installations. You don't need a specialist or certified line crew to do maintenance or emergency restorations with this type of conductor. So when we say effective protection, it means it has the ability built in to handle these bendings, to handle these extreme sharp edge situations. It has the ability to protect the vulnerable organic constituent for life, and it has the compatibility that the line crew expects you in terms of how the conductor gets worked in the field. And these are very, very important. And that's why we say that we have safety, reliability, and longevity all designed into the product.
Jason, would you mind if I move that around?
Yes, yes. Yes. Yeah, thanks for doing that.
Yeah, keep going.
Yeah. When you have the carbon composite core that does not have fiberglass in it, because this core is so strong, you can often go to a smaller size carbon core and still end up with a very strong conductor. So what it means is now you are able to open up more space, even more space, to pack in the aluminum. We actually are packing more aluminum than any other conductor. That's how you end up with a conductor that has greater ampacity, lower resistance, lower line loss than all the other conductor. And we can potentially triple the line capacity because the conductor doesn't sag. You are able to walk in a larger size conductor without violating sag, without violating tension limit to the existing towers. And you can also, we talked about the lower capex, because when you are doing reconductoring, for example, we allow you to leverage fully the existing structure in the existing rights of way, because we are able to maintain line sagging, and we are also able to maintain line tension within the limits that was established by ACSR when the old line was designed and built. We also, when we talk about climate change, there are more and more extreme weathers. Whether it's, hurricane wind condition or ice or wildfires, that resiliency aspect is also important. And with TS conductor, I wanted to make a comment about the resiliency. One is you have a conductor that is stronger, that allows you to handle some of the unexpected, like, even stronger or more intense hurricanes or heavy ice building on the conductor. Or when you have wildfires, for example, the conductor as built, without even getting into the smart aspects, we have the aluminum already annealed. So what it means is, if you have a transmission line, you've got wildfire that are passing through. Normally, you have to manage it or deal with it for a couple of minutes while the fire is burning the bushes under the transmission line. The TS conductor, the aluminum is already annealed, so it's not going to lose any more strength because it's already the lowest strength out of aluminum possible. And the conductor is also not sagging while the fire or the heat is below. So they're going to stay very high above the ground. Turn that around with ACSR conductor, which is the wires that we're currently using in the transmission lines. The aluminum is hard aluminum. When these aluminum are exposed to the heat from wildfire that are burning right below, it is going to anneal these hard aluminum. You're going to basically lose strength. The line is going to sag. And by the way, when the temperature goes up, because of wildfire, the steel inside the ACSR conductor is going to stretch. That's going to bring the conductor even closer to the fire right below. It's going to bring even more heat to the conductor. And even if the wire survives, more likely than not, the conductor is probably converted into annealed aluminum with steel inside, and you are likely going to be in violations of sag clearance. So with the conductor as is, like you are seeing here with TS conductor, it is also built in with better ability to handle the wildfires as well. And if you are able to play this video here, the first core is the glass carbon hybrid core. And when you have a sharp edge like that, it's guaranteed to fail.
No, I did it. Never sent a finance guy to do engineering work. There you go.
I hope we'll figure out a way to play. But the point is, if you do not have protections in a sharp edge like that, by the way, sharp edge too happens in the field. When you are coming out of the clamps, that exit point is a sharp edge. And if somebody is stretching the conductor below, it's going to bend. And you may not even know your conductor is compromised. That's even more dangerous. When you have the aluminum encapsulated core with the TS technology, you can bend it however many times. it's not going to matter. And the other video is actually for small radius bending. When you have the bare core, which is again the glass carbon hybrid core, it's going to snap in the bending process. But with the aluminum encapsulation protection, you can bend it many times. It's not going to matter. That's the robustness. And I hope we can get the computer to play maybe a little bit down the road. This is a comparison of ampacity as a function of temperature among all the different types of conductors. And by the way, these conductors are of the same OD, because if you compare a large one versus a small one, that's not quite fair. So all these conductors have the same conductor OD, about 1.1 inches. The golden color is the TS. We actually offer the highest ampacity, even though we are only running them up to 200 degrees C. And you have some of the other conductors like ACSR or ACSS that runs to 240 or even 250 C. They do not offer, the same ampacity as a TS conductor. Oftentimes, our industry called these type of conductor high temperature, low sag, and the perception is, well, they're high temperature, low sag. If the conductor have a higher temperature rating, they must be a better conductor. And that's the wrong perception, because if you have a conductor that doesn't have to run as hot and you are delivering the same or even more ampacity, that's a better conductor for you compared to the one that you have to run them extraordinarily hot and you're not actually quite measuring up in ampacity. And to put it in perspective, we also, we have gap conductor, we have the glass carbon hybrid core conductor here, the golden color is TS, and we have ACSR, we have ACSS. And if you wanted to see where the ACSR is, it's somewhere around here that we have the ACSR, which is the conductor that's being, still the dominant conductor of choice that we're using today. This is for a transmission line in Midwest. By the way, the old circuit is featuring ACSR drape. We normally associate something called 795. It's 795 kc mil. It's a measure of how much aluminum is in the conductor. And kc mil is a crazy unit. For those of you who are curious, it's basically 1/1000th of a square inch. And you can go figure that out. So it's got 795, I can't even make sense of the units, but 795 kc mil. You have ACSS conductor, which is a 50-year-old technology. That is also 795, so it's a round aluminum strand, but these are annealed aluminum strand, and this conductor can go to high temperature. Unfortunately, with ACSS, because of the excessive sagging from summer sag, you are only able to get a marginal increase in ampacity without triggering retrofitting the structure, make the structure taller. And even if you allow the conductor to go to 200 C with retrofitting, you are increasing ampacity from 950 amps to about 1600 amps. With TS conductor, the same 1.1 inches in conductor OD, you have a conductor that allows you to go to almost 1900 amps without retrofitting any structure. And by the way, there's actually room in sag as well as in the maximum tension to the structure. So what it means is you are able to put in a larger TS conductor into the circuit without violating sag clearance, without violating tension to the crossarm. And so here we're putting the bitten size conductor, which actually has 1620 kc mil aluminum. That's a lot of aluminum, by the way. That allows you to get to about 2400 amps, which is about 250% of the baseline capacity without any sagging issue without exceeding line tension limit. What it means is you can do it without retrofitting any structure. Our conductor can also incorporate a high emissivity coating, and what that means is it allows you to gain additional current carrying capacity without any violation of line sagging or line tension to the structures. By the way, on the line tensions, when you are exceeding line tension, you have to actually strengthen the cross arm. That is a form of retrofitting. It's going to add cost to it. And if you have to raise the height, that's a form of retrofitting that also adds cost to it. And this is a line that has to be designed to accommodate what's called NESC heavy. It has wind conditioning and ice on the conductor as well as the worst design condition. You have to meet that requirement for the region. And so with the coatings, we're able to push the ampacity to be over 2800 amps compared to the baseline that was only 950 amps. That's where the 3x capacity comes in with TS technology. And by the way, for the same 950 amps, if you pass the same current through all these different conductor choices, you actually can figure out what is the resistance. And from that, you can figure out what is the line loss. At 950 amps, both the ACSR and the ACSS conductor, they have somewhat similar resistance, which is about 0.146 ohms per 1,000 feet. You can get to be pretty precise, by the way, in the modeling capabilities, and you can do actual measurements as well. When you move to the TS conductor, that resistance drops to 0.1 from 0.15, by the way. And when you go to the bitten size TS conductor, it drops to less than 0.07. That's less than half of the resistance associated with ACSR or ACSS conductor. And this type of line loss reduction is actually very meaningful. You know, you can put a price to whatever kilowatt hours or megawatt hours that you have to compute on an annual basis, and you can figure out with a more efficient conductor like these how much money you can save for the system. Where the savings goes, we can have a discussion about that, and that's where society, our utilities and the regulators can look into, and perhaps we can leverage that to pay for the cost associated with grid upgrade. What we have fundamentally changed here are three paradigms in conductor technology. One of them is we're able to go to very high ampacity by running the conductor hot without the sagging problem that plagued the prior generation technology. Why we can do that? Because the carbon composite itself has virtually no thermal expansion. That's why you don't have a sag issue. Second paradigm we're shifting is we're able to pack in far more aluminum to the conductor without weight penalty to the conductor. Imagine normally, if you have an ACSR conductor, you want to pack in more aluminum, it means you're going to have a bigger, heavier conductor. With TS, you don't have that weight penalty. Why? Because we're taking advantage of that 80% weight saving by taking the steel out. And we leverage that weight saving for getting the aluminum in so that you're not getting the weight penalty on the conductor. And lastly, we are taking advantage of the more conductive but yet a weak aluminum from a strength perspective without compromising on conductor strength. Why? Because the carbon core is twice the strength of steel. You actually end up with a stronger conductor even though you are using the annealed aluminum that doesn't have any strength to contribute. And that's what makes the technology work. I'm going to skip that one.
Jason, if we can wrap this, because we'd like to get
an opportunity to speak, and then we can get into the Q&A.
Oh, sure.
Explore a little bit more. Is that
Yeah.
okay?
Yeah. I thought we had 2 hours, and
Yeah, we are almost there.
oh, really? Are you kidding me?
No. Yeah, that's right. It only feels like it.
Yeah. I'll just give you some examples, and then we'll wrap this up quickly. This line is for the MDU project. This line was energized. By the way, it had about 37 miles of conductor in this TS conductor in this project. It was a 230 kV line, energized March 2021. They were using ACSS for reconductoring, and they had to replace or retrofit 90% of the structures. When TS was deployed, they avoided all of that. We were able to save them 40% in total project capex. This is not my number. This is the director of engineering's disclosed information to us. And we also shaved a year in their project schedule because we didn't have to do any retrofittings. This is an example. I think it's worthy to bring that up. That when you use ACSR conductor versus TS and the TS bitten that we talked about, you are not only getting the ampacity to about 2800 amps, which is 3x, you are also creating almost $4 per feet per year in line loss savings, with the assumption that each kilowatt hour is 6 cents per kilowatt hour or $60 per megawatt hour. That's not an outrageous price for electricity. And we're using 70% load factor because it's between transmission and distribution. It's a 69 kV. That $4 per year per foot, if you tally up 20 years, that's a lot of money. That will pay for the conductor or the entire project cost many times over. If that's the money, that's the power that we needed to look at in terms of how to pay for the cost. And we don't have videos, so I'm going to skip this one. And this is our manufacturing. I'll just probably talk a little bit about some of the accomplishments. We won the S&P's award last year from Platts Global Energy, and we also won the Public Utilities Edison Pioneers Innovation Award last year, and we also won the Cable Prize from DOE last year, and we're in the final round. We've been very blessed with support from our industry, and these are the customers that we currently are working with, especially the right column. That these are repeat customers that we're working, including Mid-American, Tennessee Valley Authority, Basin Electric, SRP, APS, Nextera, Enel, for example, which is a utility based in Italy as well. And we're looking at those locations for expansion. And this is the last slide. I promised.
No, I've got a question, Jason, if you don't mind answering.
Yeah.
Before. So what do you say to people who would come to you and say, okay, your conductor is all these great qualities, but you're high in price.
Yeah.
Okay. Is that really true? And is there additional savings that can be accomplished for new projects or even retrofits?
Yeah. That's an excellent question, because the perception with advanced conductor has been they're very expensive. They're just not affordable. They're for niche applications only. We need to really change that perception, because if you look at the ceramic fiber composite core conductor, yes, there are 6 to 10 times the cost of baseline ACSR commodity conductor. If you look at that glass carbon hybrid core conductor, they're about 4x. Where TS is today, we manufacture the conductor ourselves, and we manage the cost associated with manufacturing and all the materials as well. We're about 2 to 3x. With volumes, with the East Coast expansion, we're trying to move that down towards a 2 or below 2. And even with our current pricing, we are able to compete against ACSR for new lines and against ACSS for reconductoring on project level cost. On the project level costs, I'll give you some examples on new lines in particular. We've been working with Basin Electric. They are building several 230 kV new lines, and they did one last year already with TS Conductor. What they're able to find is we can save 10 to 15% structures and also shave the tower height by 10 feet. That's how they can realize project level CapEx savings, even though our conductor has a modest premium. We also work with NextEra. They do a lot of renewable development projects. One of the projects in Texas, it's a 11-mile long connections basically tie in and 230 kV. If they used conventional ACSR bitten, which is their baseline conductor, it would have required 78 structures. With TS Conductor, we don't even have to get into line loss savings and all that benefit. We can build it with 59 structures. That's where your CapEx saving comes in. And reconductoring, it's the MDU case that you are able to eliminate all the structural retrofit, which is really where the cost is.
Yeah.
Very good question. And I just wanted to wrap this up here. As a summary, we can drive for lower project CapEx, as the question was asked, whether it's reconductoring or new lines, for higher ampacity than any other conductor options, as much as 250% or 3x if we leverage the coating technology onto the conductor. At the same time, you're getting the ampacities, you are also capable of achieving line loss reduction. That is something that society, regulators, policymakers can leverage as well. And the conductor can also be made smart. And what can that do? Well, it can do a lot of things for you. It can allow you to do dynamic line rating in a much more precise, real-time fashion as well. What we are able to do with this smart conductor is you are able to monitor line sagging precisely, real-time, at all times. You are also monitoring the temperature of the conductor itself in a distributed fashion, real-time as well. Those are the two information you need to do dynamic line rating. And some of the dynamic line rating today that are out there, you require major assumptions. You do one-time flyover, you assume that condition of line sag applies to every day, which is not true, by the way. You will also be able to monitor line conditions in a smart way. For example, we have crazy things like people are shooting at the power line as target practice. Let's say you've got a conductor that are partially damaged. You will have a hot spot. Or you got a vegetation event, the tree branches is on the conductor, or for whatever reason it is creating a cold spot. With the smart conductor, you will be able to know as these things are happening the first time, and you can dispatch people to the precise location, getting that fixed before they manifest into something much more serious. You can also monitor the impact from extreme weathers on the circuit, because you are able to monitor how much ice is building, how strong is the wind blowing at it, where in your power system that are getting affected by these extreme weathers. And we talked about the wildfires. With the temperature monitoring capability, you are actually, from the control room, be able to read where the fire is, which circuit is affected by it, how much is affected by it. And when you are doing power outage, you are able to do it in a much more precise manner instead of doing in California, we have this PSPS that no one likes. Whenever there's a strong wind forecast that, you get a voicemail from recorded voicemail from your utility supplier saying, hey, your area is subject to outage. And by the way, all of these don't mean a thing if you do not have safety, reliability, longevity. Why? Because we work for the utilities. Safety, reliability, resiliency, and there's also affordability. They all come into play. So thank you. I spent a lot of time, so.
No, this is perfect. Sir, please. Thank you, Jason. I don't have any slides. We can leave that there. We'll leave it up there. Again, I'm Terry Donnelly. I'm retired from Commonwealth Edison in Chicago the end of the year after 40 years in the biz. And Jason, it's a great presentation, and I thought it really hits key messages. I could even maybe throw you a couple audible questions while I'm up here. But the issue of advanced conductors, I've been on this for a while. I ran into Jason, a number of years ago, and originally CTC, which is the carbon-based, and actually I showed up to your factory unannounced one time, and that's when you were running CTC. Yeah. And then, so, this area is starting to explode, in terms of advanced conductors. And it's something that the industry will need to accelerate their approach to. For a variety of reasons. Losses, electrification. You're not going to build any new lines, certainly not in the U.S. Nobody will let you do it. So you got to get more out of the existing corridors, and you can't be replacing all the towers either while you get more capacity out there. So at ComEd we have about 5,800 miles, which is a lot in one jurisdiction, because we go to the Mississippi River, the Wisconsin border, and almost to central Illinois down in Springfield. So a couple of points in Jason's presentation as he was going through there, the word, one of the fiber was delicate, and delicate's really a bad word in the utility business with working with line crews. They are not delicate. All right, so the old story with linemen is they tighten it until it breaks, and then the next time they just tighten it a little less. All right, so you really got to deal with that, and we saw that in the presentation they deal with that. I took an away team up to North Dakota. Wow, talk about that area. And where Basin Electric Cooperative was putting this stuff in. It was a ragtag contractor crew. A lot of times they don't have the advanced trucks and all. The utilities can kind of maybe get more. It was ragtag is a little harsh, but they were putting this stuff up. I think it's 27 miles, and they were putting it up with very little problem up there. And it was good to kind of have line people talking with each other on how it is to work with the conductors. I think there's many good aspects of this conductors. The competitive field is increasing. The business case is clear. Production costs have to be driven down. The love affair with ACSR continues to this day. As big utilities were, been tagged with slow to change. Sometimes there's good reason to that. I mean, in the cell phone industry, you can take a couple of drop calls. You really can't do that on a power grid, the equivalent of drop calls. There's very little forgiveness. There's a downside. I mean, there's been a lot of innovation in the power grid. There's a downside where, okay, got some good conductors, Jason. Well, let's put it up, put it there. Let's do some aging testing. Come back to us in 40 years and see how it performs. I think it's a little harsh too, and there's accelerated aging as well. But there's a lot of culture in play here. And as someone who was president and COO, I could say, well, I was the boss, and it's hard to get people to change. So the transmission engineers that are not that old, they're certainly a lot younger than me. And I'm kind of like, where did you get this old thinking? I should be the one with the old thinking. And they're like, well, we're putting up ACSR. We have to drive the cost down. But, there's a lot of junk out there that's cheap and affordable. So it doesn't always mean it's affordable when it's bad. And we have to keep getting to this overall value and doing it right the first time. That's easy on greenfield, doing it right the first time. It's a little harder on legacy rebuilds. But the loss issue is intriguing. Jason claims that you can really almost, quote, finance the line with loss reductions. And I'm like, no way. We've talked. I'm just kidding. It's not that we haven't discussed this. Because you're telling me reconductoring a line, that's heavy labor. I don't care how many towers you're saving on that. That's big stuff. And that CapEx is not a small number. And you're going to really drive loss reduction numbers. But when you look at it, 20, 30 years, the thing is the policy's not quite there on losses. I call losses it's like blood pressure, high blood pressure. It's the silent killer. It operates under the waterline. Losses are losses. The hell with them, right? They get thrown back in the pie and everybody pays for them. You just get thrown back in. And sooner or later, we're all going to wake up to losses. It's just a matter of time. We see it more in Europe, Italy. We see some of the amorphous transformer standards starting to come out. We see Enel changing every one of their transformers. Get out of there because of loss standards. Not so much line, but loss transformer standards. It's coming. It's just a matter of time on policy to provide perhaps more incentives for get the right thinking with losses versus you just throw it back into the trash can for everybody to pay. Because there's real there's real GHG in that and waste. Now the other benefits as a hardcore utility veteran, resiliency, reliability, 2-3x combined with dynamic line ratings is not as far along as we think right now, but it's getting there. It's for 888. To have true dynamic load ratings is, we're getting there, but it's still in its infancy, despite what anyone says. But then you get into scale, okay? So maybe you can solve the loss problem and drive some production costs down. You can have kind of like hardcore linemen put it up without much science projects and advanced certifications and degrees. But when you look at scale on these transmission systems, you're still talking big bucks. And, is it needed? Of course, it's big bucks for a lot of stuff for the future. That's not even talking about the distribution system, which there is some TS conductor possible uses on distribution with nobody's really kind of cracked that nut yet on distribution. So now you're talking hundreds of thousands, of miles on that. But we're going to need something there too. And new distribution standards on pole standards and composite and steel and things like that. So then you get into the overall affordability, in terms of, and, there's a lot of competing wins out there between regulators and the cost of service and what's really required to achieve a future of high penetration renewables. And at what cost? And there's a cost. So back out down to a little broader perspective. at Commonwealth Edison, I've been at PECO 21 years. I came to Chicago in 2000, late 04, 05, and it was like a disaster, and there were so many legacy problems. I actually came in a big tunnel fire for 10 138 kV lines underground, burning to a crisp on my first day with my family in the car, and it wasn't a good car ride from Philadelphia. But we worked over the years and the decades to orchestrate a change, both employees, reliability, resiliency, investment, where we were, which I was fortunate. At the end of last year, we were named the most reliable company in the nation when we were one of the worst, and by the Reliability One Awards. And it's backed by hard stats. Whether it's safety, Katie, resiliency metric, gray sky days, repeat interruptions, the list goes on and on and on and on. And so we were named that. And so we've achieved good things. But when you look at the numbers that we've achieved, we've only gotten to the starting blocks. Okay, that's great, most reliable. But when you look at what's required for the future, whether it's conductors or what's required with high electrification and resiliency and reliabilities, we have now only took 15 years to get to chapter 1, or maybe the preface in where we are now. You look at some of these international utilities, like Japan, I mean, we're like a third world country. And when you look at the U.S. companies generally, they're not that great. Okay, we're the best of the not great. Okay, I'll take it. But, it's, you look at somebody, the California, who would have thought today with all the advancement we'd be dropping hundreds of thousands of people off from the wildfire. Who would have even dreamed that would happen? So there's a lot going to need it to take reliability to crank it up to the next level. And it's not just 2-3x on transmission capacity. We have a big transmission. It's also 2-3x on reliability, resiliency, distribution capacity. And then comes the regulator. Now you got a patchwork in the U.S. of co-ops and munis and investor-owned utilities. Sometimes the munis and the co-ops can move sometimes a little faster. The Basin Electric Cooperative, they're taking his conductors and just stringing it in the air. Hey, we're just going to do it. Because they have a little more in the regulatory framework to do it. But when you look at our business, we're completely regulated. We are a completely regulated business. You can thank Sam Insel of Chicago for that. Actually, there was a lot of good reasons for that. He was our founder, and he did a hell of a job in promulgating the modern grid at Fisk Generating Station, the economies of scale, central station generation, the role of a regulator, the role of natural monopoly, stuff that have lived through this day for the benefit of pretty much the nation when you look at it. But our economics are fully regulated, right? Not just like airplane maintenance is regulated. Our economics are regulated. So this inherent tension, one could say it's like company unions, right? It's like company unions, there's a saying in labor law that it's inherently adversarial because that's what makes it work. So, in the regulator and all that, it could be a little harsh to say it's inherently adversarial, but, there's something to that. Then one could argue that's what makes that work. But the case for big juggernauts like Commonwealth Edison is to have a more aggressive persuasion. I'm almost talking like a politician, right? They persuade. And a more aggressive persuasion of what it takes. Because inherent in our relationship is you just want to spend more money. Because Sam Insel said you make a return on capital So you just want to spend more money. And we don't think it's necessary. Case in point. So when you look at our reliability journey, there were more problems than you could, bad design. Bad design, let me tell you, design is almost everything. Because what happens on the drafting table is the cheapest type of productivity you could ever achieve. Ever. And there's so much was bad design. And then material conditions. So our transformation had to be regulatory support, a massive prioritization, monstrosity of prioritization skill set. The cable systems were broke. We improved cable reliabilities by 71%. Mainline cable, we refurbished 32,000 manholes. URD cables, it was junk when it was put in the big build-outs of the late 60s, early 70s for a variety of reasons. Had to have 48 boarding crews come in and replace most all of it. And it's still not done. It's almost done. And those faults have come down about 5,000 to 2,800 a pop. We're talking big money. So what we now have to do, and now we're into multi-year rate cases, is really have more partners, which we have. We promulgated 24 grants with the Department of Energy on advanced grid technologies and a whole list of technologies on how this stuff works in harsh environments. Jason talked about that. We're not a lab. We're the real world, and it has to work in harsh environments. And that's our job, is to partner with the Jasons of the world and others to say, will this work for real? And none of it does. Sorry, Jason, I didn't quite mean that personally. But the new technology, it doesn't work. All right? In the beginning. It just doesn't work. None of it works. I've been saying this for a while. I say that from experience. Because you take this stuff and you put it in downtown Chicago, and then our static VAR compensator, synchronous machine, all these new stuff you need for grid variable volt VAR systems and things like that. And man, you have to partner with these vendors, and you have to aggressively spend months to try to make it work for real. As spec'd, as designed, as delivered, nah. No, hardly ever. So this is our role in this transformation in terms of big utilities, small utilities, whatever, is to really partner and make this stuff work. What are some of the things that are needed in the future? A whole bunch. The one I'll talk to is you got to implement advanced technologies. And you got to try to keep building on it, the legacy stuff works with the new technology. You're really rebuilding big urban grids that are energized, right? You're rebuilding it. It would be great if you could just tear it all down and start from scratch. But for an old system, we have reports written on this recently. They're all public. I think the word that commented is an old system was in the report like 70 times. And then it said, wow, they really performed well for an old system. So we took that actually pretty good. It's kind of industry leading. You're in the lead. And it's an old system. I tell you, that's a challenge. So you're trying to rebuild a grid while it's energized. You're trying to arm wrestle ring buses, breaker and a half schemes on old straight buses while the substations are energized. And reconfigure these stations to be, quote, smart, advanced technologies and things like that. The DA schemes and has been instrumental. The DA, what we need, and I'll close on one technology. In this future world of high penetration renewables and real-time situational awareness, and to make it all work, you need an advanced communication system. High speed. We're used to that on transmission. We're no stranger to fiber, okay, and putting it in. But we had, or do, or have, I'll just keep talking like I'm there, an aggressive build out of a fiber system called REACTS, and I forget the acronym. First order of business, make sure it's a fancy acronym, helps get approval. But it's advanced fiber because you need an advanced high-speed communication system on the distribution system, not transmission. You've got to bring high speed to the distribution systems. You just got to. You need to, in the ultimate vision, to move transmission clearing down to the transmission system, which is orders of magnitude, right? You're talking about 3-4 cycles on transmission. You got to move it. Ultimately, you want that clearing. You want only DA devices to open where the fault is and everything else stays on without a perturbation and knock solar offline or big manufacturers. You want to, so we're kind of been putting this in, and the beauty is you can take these legacy DAs, the Vipers, the SNC, the Interrupters, other vendors, and you can take that fiber that's currently on mesh networks on AMI, and that fiber comes through, and then you're upgrading the system to grade B while you're marching through the system with fiber. What's that mean? You're putting bigger poles in, different cross arms, fiberglass arms, so you're kind of hardening as you go, like an infantry. And then you're putting the fiber in, and then you're coming through, and then you got to do your engineering on the connectors, and you put the connected fiber into the DA systems that are there. Legacy, you don't have to replace it. And then you get these advanced schemes tied to substation breaker that start clearing faults like it's a transmission system. And that's not even mentioning all the renewables, data, situational awareness, distribution PMUs that you're going to need, things like that. Okay, it's all there. Now, the other thing, with this vision on this communication system, and you're going to be working, it's all the end use cases. There's 19 use cases to this, right? It's not the fiber itself. And quite frankly, fiber is still the gold standard. And you put and when you put a piece of fiber in like this, you might as well put a piece of fiber in like that, because the line crews are all embedded costs. It's just, you know, ragtag line crews. They just say, no, it's bigger, I'll put that up too. You know, it's really, then you can help with the digital divide if you get innovative policy with internet service providers on that. But that fiber's yours, all right? That's got 19 use cases on the grid, end use devices. There could be power quality, resiliency, high speed, clearing, things like that on that. And then in the end, okay, we're talking maybe 10, 15 years, you've got a fault current system. You have a distribution system with half of the fault energies, with fault energies cut in half. Now that's going to be a game changer, not only for safety, it is for safety, both line crew safety and public safety, but the stresses on the system from a 50% reduction in fault duties, the stresses on the system. Those you see faults on distribution system, those wires bounce up like there's no tomorrow, and they ripped off the insulators, you know, and you run for cover. So you lower those fault energies down. Then you get the higher speed clearing. You get the solars to stay up. You get all the situational awareness you need for that. And the case is, how do you keep persuading people that that's what's needed? Why are you putting fiber in? You shouldn't have put fiber in. You don't need that. You don't need that, right? Fiber sounds like that's not your business. Well, you know, this is the case for the future on how to articulate how we're going to get there. And back to losses, the citizen utility people are kind of like tongue-in-cheek, call them the enemy. They're not. Citizen utility boards, the consumer advocates, they're actually on to these losses. You say losses to them, they like Volvar. They like Volvar because of losses. And you're like, why are you? they see that as greenhouse. They actually see that, and the utilities don't, right? Because the regulatory model's not loss friendly, on that. And then finally, with underground, everybody wants everything underground. More and more that's going to, you can't build a new line. You'll be hard pressed to build a new underground line. You can put these high voltage DC cables in big right-of-ways, but Jason, to these advanced conductors, you got these towers, you got these right-of-ways, they're not going to be undergrounded. Okay, so PG&E says they're going to underground all their or a lot of their transmission systems.
Distribution.
No transmission. No transmission. Okay. I don't know how that's going, but
$40 billion estimates.
Right.
Only.
If it was new, yeah. And do you change the standard going forward? Maybe. Never underestimate the value of changing the standard going forward. It's tenfold what you think, and you always think it's not going to do anything because in your head it's all the craps that's already in there. And you say that won't make a difference. Well, man, it makes a huge difference on that. But underground stuff, Jason's talking a lot, on the overhead. We got a lot of work by the big underground manufacturers of the world to try to, you really need, ComEd got away from the high pressure fluid filled systems early on that Con Edison held on. And we got on in the 90s when we partnered with the likes of a Prysmian to come up with solid dielectric 345. Really led the industry and moved off that standard of high pressure fluid filled back in actually the early 90s and did rings around, double rings around Chicago with the solid dielectric. But you got to get a technology. Maybe Jason will figure this out when you foray into underground. You got to get the rating of that. You got to be able to replace high pressure fluid filled cable with new cables that can fit in that steel pipe that the high pressure fluid filled cable is in. And so far, it's a tough nut to crack because of the rating that you need to do and the cooling, the performance to get it in that 6-inch, 8-inch pipe that is fluid filled. And you can do that. You can replace them all, get rid of all the pumping plants and things like that, and maybe of a technology to get you a 2X for something like that. Now, Okanite, and they're working some of it down south, but they have nowhere near there's some promise that they're nowhere near the ratings you would need big city like Chicago that you could be. They're kind of like doing it on a lower scale. So a lot needed in that area as well. And I'll just stop there and go back to Ali and see where we want to take that. And
we've got only 3 minutes, so we'll open it up to questions. So, folks, any questions?
we're till 9:30.
9:30? I thought it was 9.
No, 9:30.
Oh, we're good then. All right, so perfect. Like ours is very simple. We are just finance guys. However, unlike a typical PE company that only does financing, we have transmission in our, as I said, in our DNA. So we do, open transmission. We do greenfield transmission development. The 10 West, Hudson, these were all Neptune. They were all greenfield projects, and we are actively participating in open markets. FERC 1000 really opened up the space for transmission development for independent transmission developers. Before that, it was completely the domain of the incumbent utilities. Now, what separates us is from a typical utility development is that we don't carry the utility overhead during the development cycle. And, Terry accurately pointed out all of the, the structure, the utility structure, the model. That is because that model is not in very efficient model. It was perfect for when you were developing a transmission grid, because what was happening is when, for those of you guys who know the history of the electric grid, when we were starting, you needed to provide incentives for the company to build a system that will support a growing nation. So,
And it would last 40 years.
and it will last 40 years, exactly. So what they had to do was to spend money before the need came through. And so that's how the whole, natural monopoly concept came about. Now that had its benefits at the time, but now competition is the key word. However, the utility structure that the states have been adopting or has adopted, which was a long time ago, actually forces them to be inefficient. Okay, it's not what they want to do, but it is, their structure is designed that way, and it is monitored by a lot of the state regulators to be at that such way. So this allows us opportunities to independent producers to come in and be cost effective. And with FERC 1000 projects, it allows us, it opens up a landscape for independent producers to compete directly with the utilities. Now I'll give you an example of how effectively independent producers have competed. So my experience has a lot been in California, and California has truly adopted the FERC 1000, the essence of FERC 1000. It's open solicitation. In the last 3 RFPs, not a single incumbent utility have won a single project. It has all been independent producers, and the costs that have been for the winning bid have all been less than the Cal ISO estimate by significant amount, 20-30% lower, and those projects are being built. So this is the landscape that we play in, and we also, but at the same time, we know that there's a lot more required. There's a Princeton study, if you guys ever want to see this, it's indicated that you have to almost triple the capacity of the grid. As Jason pointed out, as Terry pointed out, you have to triple the capacity of the grid to achieve by 2045, to achieve the aggressive carbon reduction and the renewable energy goals that we have created. Now, you have a grid right now, and the grid was designed for a very particular purpose, and it was designed. And at that time, when the cities were growing, your power plants were really at the outskirts of the city. Actually, the cities grew inside the power plants, and what we ended up doing was serving the load from the combination of the transmission coming into the cities, plus the internal generation. Now what is happening is these internal generation, which is already 40, 50, 60 years old in some cases, is all retiring. So all of this energy has to come from the outside, because renewables you can't locate where you have those power plants. So now you have to redevelop the grid and build it up and bring all of that energy in. And as Terry pointed out, you are now taking a square peg and trying to fit a round box around it and see how we can best do it. So that's the challenge that we are facing. Now, in this room, how many transmission developers? Anybody? Anybody developed a transmission line before? Okay. Anybody got a root canal ever? Okay. Just imagine if you want to develop a transmission line in the heart of San Francisco, and a choice between that and a root canal without anesthetic, guess which one you should prefer? Okay. It's challenging. And that is, to say it lightly. Transmission. The only thing you can think about transmission development is it's always going to cost more than you think. It's going to take longer than you think, and it is going to be more painful than you imagined. That's it. And that is because
Sounds like a lesson from life.
Yeah. but that's the reality that you deal with as a transmission developer. And but at the same time, it needs to be done. So we prefer partnerships with technology providers, for partnerships with RTOs and utilities, okay, where we think that we can bring the synergies, because there's so much that needs to be done. No individual entity can provide that service. So you have to be partners, because where Jason can bring the technology, Terry can bring the right-of-ways and the access to the right-of-ways and the interconnection and the knowledge of the grid, where you actually need to be. What is the best option? And a company like us, what we bring is, we bring the efficiency of development and work with the partners, work with the internal structures that they have, so that it fits, so we can best fit their square peg in the round hole and yet achieve the goals we are trying to accomplish. So with that rant, I'm going to ask a few questions. Let's have a dialogue, and if there are any questions, please feel free to jump in. Okay, so first of all, any questions that have emerged thus far?
Terry, you mentioned we're not as good of a utility as like Japan. Is that because of regulatory, or?
That's a whole bunch of things. I mean, it's never one thing. I mean, if you look at Japan, first of all, it's a predominantly overhead company. Everybody thinks it's all underground. You look at Tokyo or something like that. But I've been there. I work with TEPCO a lot, and I've been there many times. And they've been at automation since the '60s, early '60s, in automation. So they've been at this thing for a while. Plus, there's not a wood pole in the whole of Japan. It's steel and concrete, right? And if you look at their connectors and all, and you look at their streets, it's like all overhead. So there's no steel, there's no poles. I don't know how much of that was hardcore engineering. It was on the DA. On the poles, I think they just didn't have the wood in Japan, so they went another way. In terms of regulation, not so sure about that. That was a key driver, but they've been at it pretty well. And you look at TEPCO in Korea. You look up in the air. They run fiber. I was like, man, they're already on fiber. Now it's not a big fiber, it's like old. It's in that twisted thing. It's just like a piece of fiber. They're DA already all on fiber. I don't think they have the fast clearing schemes that I'm talking about in the long-term vision. But I think we got to really do a better job of seeing what everybody else is doing in the world. I like your point about partnership. We're all good at certain things, like utilities, Jason, Ali. We're all good at certain things. Sooner or later, it's got to be like Uber in New York finally getting together with the cab companies, and they finally came together. And so that's where I think all of us in the future, we're going to have to come together to leverage our strengths. We have sort of the right-of-ways, we have sort of the long view on, hey, if you do this, we want it built a certain way. We want to build it for double capacity, even though, where we need to do it that way versus single line, some stuff like that. But I think we just got to all realize we're certainly not, in my view, that great in reliability from a global thing. I mean, we're probably on par. We're better than France. We're UK Power Networks in London. We're probably with them, and maybe Sydney, Australia. We're probably with them. But a lot of the Asian companies were not nowhere near that.
By the way, one of the most interesting things I ever saw in Japan, I saw a tower with 14 circuits. Yeah. You will never see that in the US, like 14 circuits. I actually had to request our cab driver to stop so I can take pictures. So, anyways, ma'am, you had a question.
Yeah, I just, the conductor presentation, you talked a lot about the cost and how you're paying. And on this side, we also have greenhouse gas savings.
Mm-hmm.
Do you see an opportunity to leverage some of the greenhouse gas grants and other financial programs with these trust rates?
Jason?
Yeah, there is some discrepancy in terms of policies from the United Nations. For example, if you have the projects in developing countries, all these efficiency-driven greenhouse gas emission reduction can be tradable carbon credit. But if you're in the developed economy, there's a different understanding and a mechanism, and I think people are still trying to figure that out. Let's say if we have a more efficient conductor in the U.S. circuit, how the greenhouse gas emission reduction can be a credit and how that can be, traded. That is not settled at this point. I think that would be one more financial incentive in addition to the line loss that Terry talked about, that Ali talked about, that can be leveraged to at least subsidize grid upgrade costs.
But I like what Alec said, from the old deal with Sam, our guy, Insel, about the need to build it before, right? And
The
just to
need
build
to-
it, you come, right? So who's making money on building a line right now? Today, there's some markets that do it, but back building lines to electric, you're building a line. So you needed a different model or rate of return and things like that. You're not doing it for fun. You're not like, you gotta have some mechanism to earn on that. But we're really back to the future, because now we gotta pre-build. We're back to pre-building. You gotta pre-build. We transitioned to need, right? Okay, well, there's a big ADM flour manufacturing. It's in Mendota, the biggest in the world. Okay, there's a need, and now we're gonna serve that. Well, that whole thing's blown up with data centers and all like that, and they want it tomorrow. So you're busy running the jumpers off transmission lines until you can work 3 years to get your substation reconfigured to breaker and a half, double, schemes to feed it reliably. So now you're back to the future with you got to get building before it happens.
Right.
You're back to the electrification, right? Because you can't. Then it's all become a debate on how fast it can happen. And is it really going to happen? One camp says, yes, it is. And then you get naysayers and rate cases. They're always overestimating EVs and all like that. It's always less than, would you say, slower. Hofstadter's law is things take longer than you think. Ali said, the longer, the harder. And so, but we have to get back to regulatory constructs about the need to get stuff built before, what happens, like we had to do in the 20s, 30s, and 40s.
Right.
And then we're now need-based now. Everything's a need. Well, do you have a need? Well, yeah, I got a need, but I can't do it in a year. They want it next month.
Right.
So
Now, a typical transmission line, just for reference, minimum, if you have any significant voltage, and Terry, correct me if I'm wrong, any significant voltage that has even moderately challenging terrain, 10 years. From the time you pick up the pencil to the time you energize it, 10 years. Now that's a fast development cycle. It can be as long as 15 years in some cases. It's not for the faint of heart. That's why you only see highly capitalized, specialized companies attempting to build transmission. When renewable industry started, two guys with a bicycle shop and some real estate experience, just said, oh yeah, all I have to do is go get land, okay, and I can develop this project, and that's how it started. But if you go backwards, power plants, they were only developed by specialized companies. Mom and pop shops just could not do it, okay? The same is true for transmission. If you are just, if you just think that oh yeah, I can get land, nah, you can't. So it's very specialized industry. Now, Terry pointed out something really wonderful, is that when we used to do planning, so I'm one of the laziest guys you'll ever meet. So I went to engineering school, and I picked electrical engineering. I picked power in particular. So I specialized in power because I figured they have not done any last technological advancement in our industry came with the advent of transformer. So I figured I was pretty safe. I don't have to learn new math. I can just cruise
Well,
through
you
my
were wrong.
you know, so, but structure also changes, like the regulatory structure can change everything. And this is where we are right now. So Terry, opening up a question for you. What regulatory structural changes will you make in order to, first of all, like in order for regulators to accept that we need to do things faster? What are the things that
Yeah.
need to be done?
I think our journey through regulatory space has been pretty impressive. If you go back to the Energy Infrastructure Modernization Act in 2011 in Illinois, that ushered in significant investments to start this journey to best reliable utility. And it really had several tranches to evolve the regulatory model. It made a distribution formula rate versus this rate case. So it's every year it was a formula. The ROE was a formula tied to the 30-year treasuries plus 580 basis points. And then for a while the treasuries tanked, so it was like bad time. But we lived with it. There was certainty. There was certainty and your word efficiency in the regulatory space. Okay, so, and then the next one, Future Energy Jobs Act in 2018, got some other things. Decoupling, okay? It's kind of an old school method of kind of decoupling. You true up the actual usage of what you need versus you're not. It's really the consumer's taking the risk, not the regular decoupling. But it insulates you from load decrease and load increase, which is healthy, from our perspective. You also got energy efficiency explosion in that regulatory. So the policy around incentives and earnings for regulatory energy efficiency. So it made energy efficiency like a pole, like a wire, and a cable you earn on it as CapEx, okay, versus an O&M pass-through cost. All right, so that ushered in an explosion in energy efficiency, which now that's evolving from caulk and window seal, that's what it used to be,
Right.
Put in utilities, to high-tech engineering. That's kind of cool where that's evolving to. And that regulatory policy, helped in that. Then there were incentives for achieving the target. And add to that, they made VAR programs, which don't require in consumer behavior. They reduce losses 2% on the distribution system. That allowed that to be treated as an energy efficiency investment. This is this concept of energy efficiency or loss reduction.
Yeah.
It has happened, versions of it, like in energy efficiency, VAR, in terms of counting as an energy efficiency program. You could count this as an energy efficiency program if you can open your mind, in terms of
Yeah, Terry, on that note, are these efficiency policies or mechanisms developed by the utilities and advocated to the PUC, or from the
Here's the
state
thing, for
legislation?
Illinois,
How did that happen?
it's different than other states. Well, because we're Chicago, we're not normal. It is different. It's the utility took a more active role and goes to the legislature, okay, not the regulator. And there's a lot of reasons for that, and getting our head handed to us by the regulator so many times. We said we got to go to the legislature to get laws for this stuff. So the policies I mentioned are legislative
I see.
driven, and they were part of big packages that gave ZECs to nuclear power plants to keep them from closing, and then another evolution of the ZEC through credits on the last round of the latest round, the final tranche of regulation, which remade our regulatory model to a 4-year future rate case, and then all kinds of external engagement and additional credits with nuclear power, and that's what we're living in now. Now, other policies that are key for utility is true up to actual cost, because things happen. So some of the regulators, there's a not liking the true up. But true up is a very healthy regulatory where you get hit by derechos, and hurricanes, and things like that. You get true up to actual cost. All right? Looking back, true up, and then future investment. The thing with the regulators will say, well, because you have a 4-year certainty future rate case, you have more certainty, so we're going to cut your ROA, which this happened in Illinois, which was not healthy. So these are some of the in the future, I think efficiency, additional broader views of efficiency would be needed, and perhaps more in loss reductions, more formulaic perhaps recovery systems. So it's a machine, machine of being able to, and that's where it was from 2012 to 2022, was this sort of machine. We still had regulatory review, but it was super efficient in terms of investment. So those are some examples.
So Jason, turning to you, Terry talked about about changing the world changing and the whole everything changing with it, the technology changing. We have seen that, the mindset changing. And Terry, I'll come back with you on a very specific question on that one. But take it to the next level. Let's start on the regulatory side. What do you think is required from the regulatory, from the policymaker point of view to incentivize the change, incentivize adoption of new technologies into the grid? What needs to happen? If you were the king for the day, what would you do?
I think there are several aspects. Maybe we can start with the efficiency. What Terry described in Illinois, it is probably the efficiency in the consumption side that become bankable.
Yeah, right. Except Volvar, which is a foray
Yeah.
into something grid level for loss reduction.
Yeah. I think if the FERCs and the PUCs, including state legislations, if they are becoming more aware of the economics from line loss reduction, a lot of it is really about awareness. Either the utility bring the awareness to them, or the technology companies like us bring the awareness to them that the right policies are in place. In the past, the conductors, they're always ACSR. There's no sort of efficiency aspects to it. Now there are options. I think that needs to be looked into. And in terms of incentives, what if we say, hey, let's give the utility a third of the line loss reduction to reward their shareholders and pass the other 2/3 to the ratepayers? I think you're going to get everybody on board, because you're leveraging technology to get everybody better off.
In Illinois, it would be, and this is not bad. It would not be keep a third. Is roll it back all into the
CapEx base.
The base, and rolling all the lost savings into the consumer. Okay, which isn't necessarily bad, because that's kind of like a little bit of our model.
Yeah.
And if that is persuasive for the investment, there's nothing wrong with that.
Yeah. So, and then the other part I would like to see.
Jason, before we go any further. Okay, so I'm a regulator. Okay, I'm getting this pitch about 5 times a day from every technology provider, who comes in and says, my technology will not only do all of this, it will even make your evening dinner so you don't have to worry about it. Okay. How does that education happen from a utility side and from a technology provider side, so that they can get their teeth around something? Because regulators' incentive is to reduce cost for the consumer.
Yeah.
So how does
then you get into least cost, maybe worse value. Hey, ACSR is cheaper. Well, like I said, a lot of junk is cheaper.
Right. And it's all about today.
And not the future. You're
not the future. It's all about today. So how do you change that?
Well, I would comment, first of all, maybe the Terry Donnelly answer of none of this stuff works. Remember that? It's not, you can't really say that right away. So when they say, oh, this person in Silicon Valley promised the world this technology, I could say, well, it won't work. But I think we have 24 grants with the Department of Energy. So we've now partnered with a regulator to start educating around how are these going. They're real world applications of master grid controllers, distribution PMUs. We have RTDS labs we built, to test this in the lab first on our turf, and then we run tours. So it does start with explaining the pitfalls and how we make this stuff work. We have a microgrid we built on the south side. It's kind of a living lab of stuff. So it kind of is. It's an investment in collaboration, and utilities historically weren't really good at that. But now we got to be 2x, 3x, 4x, 5x in collaboration and partnership, and we're learning. We're actually doing.
Yeah,
So
I think-
Jason, how do you go about
Yeah, I think entities like EPRI, entities like DOE, they can play a much more impactful role because our utilities, like Terry was saying, you got investor-owned utilities, munis, and the co-ops. Everybody is king in their own domain, right? Everybody wanted to do a pilot, as if they cannot learn from each other. Okay, ComEd need to do a pilot, and TVA need to do a pilot, and it's like
40-year pilot.
Yeah, 40-year pilot. I think there is a better way to move forward. The other issue is about the perceived risk. There is the actual risk versus the perceived risk. Utility has a perception of perceived risk. Regulators also have that. And how much the risk, let's say, the regulators can encourage utility to take on without overly burden the ratepayers taking on these risks. I think there are some discussion on that topic as well.
You got mechanisms of what is it? In FERC, you got if it doesn't abandonment costs.
Abandonment.
So we put
19 filing.
Yeah, we put so
Abandonment plan.
there's maybe a policy space for abandonment.
Abandonment
recovery.
plan,
Yeah, that could help with that. It's drilled into our head before we were born that we own the reliability and performance. You don't at all, right? It's just drilled into our head.
Right.
So that's good and bad. So these are some other we put a superconducting cable in downtown Chicago. It took us 5 years to get an agreement with AMSC and their partners in Department of Homeland Security, a liquid-cooled nitrogen, underground superconducting cable that wields excess transformer capacity between stations. And that's actually a whole new topic of how to better utilize transformer capacity in a more way. So we put it in, we finally got it in service. It's a 12 kV level, it's a superconductor, and we got it treated as a transmission asset.
Gotcha.
Nice piece of regulatory work, which means it gave us comfort if the thing didn't work with abandonment.
Now, just a shameless promotion. One of the ways that we have that we work with Jason and his team is to address some of the risk factors because operators are inherently risk averse because an operator takes a risk and everything works out, nobody will ever know about it. Okay, but if an operator takes a risk and it doesn't, Chernobyl. Okay, so the risk reward factors are very, very large. You can black out 14 states on the wrong day if you did not take the line out. So one of the ways we have addressed the risk part for the utility is that we have partnered with Jason's team, and we do that with other technologies as well, where we'll come in and we'll finance the development, we'll finance the project and keep it on our books and take the savings from the line loss savings in some cases, or from the take the savings from a long term just on the line loss or some efficiency savings, and then turn the project over to the utility once we are done. So that way the risk goes to a company like us. So in addition to technology, there are financial instruments that can be put in place where, going back to the collaboration, where we can all work together to protect his ratepayers, his customers and ratepayers, use his technology and bring it all together. Now, again, this is just one example of what's happening in the industry right now. Okay, so the 100-year-old industry is at the precipice of complete revolution. And the revolution has begun, and it is not going to stop because there is a recognition and an acknowledgement that we need to change in order to achieve the goals of tomorrow. So with that, if there are any last questions, we are at 9:28, and I wanted to close it right on time. So questions?
I want to fantastic presentation by Terry and Jason and yourself. Appreciate that. There are quite a few different areas that we're discussing about, and you basically mentioned about the TUC involved. We're talking about smaller district IPPs involved. So there's quite a the format that you have is very good. And normally at the conference here we have individual presentations, discussion, very useful. So my question is, in terms of the future as we go along, maybe we can get other panelists from the PUC, the regulator group, or the IPPs. This is kind of new and a new subject that we're involved in. So anything that we can say on that, really good presentation. Although we couldn't get Charlie up in here, so he would have done a similar job. Terry's done it.
No, I think that will be fantastic. Now, I must say that the PUCs, you know, their job has got to be one of the most difficult ones, because they are trying to balance state policies, you know, an existing regulatory framework that doesn't change that easily. And, you know, even if you get the staff to agree to you, you know, and again, I do not know
This
that.
is a key point.
Yeah.
Yeah, I know where you're going. Even though you hammer out the staff alignment, doesn't mean anything.
Yeah.
And it used to mean everything.
Right.
And then the ALJ decision used to mean everything. It doesn't anymore.
Yeah.
And we need new ways to look at that. This affordability, we all have to step up more on the affordability aspect of this grid transformation. We know there's real costs, but there've got to be innovative ways to drive the cost down and help protect the
Absolutely.
consumer innovatively.
Yeah, I
So-
would add the urgency as well. If you read the stories, you know, we have the warmest temperature on record in 2023.
Yeah.
The Earth is also losing about 400 billion ton ice every year. We do not, as society, as humanity, we do not have unlimited time to address climate change. You know, we have to do that affordably as well, as Terry is saying. People are already sensitive. Last year or last 2 years, when the gas price went up, the electricity bill went up, there were a lot of frustrations. Imagine, you know, the 40 billions that you mentioned about PG&E is pushing to get adopted. All these trillions of dollars we have to invest in grid, how that's going to affect the power price. We have to do that urgently, and we also have to do that affordably as well.
And just the one thing, sir. I love my regulator, but the 11 more dangerous words in English languages. I'm from the federal government, and I'm here to help. That is very true when it comes to transmission development. And if you want to solve your problems, you know, I'm an atheist, so I always say I don't raise my hands. I just look in the mirror if I want to solve problems. And I think that's about, you know, we have to come together as an industry. And if we can come up and solve our problems, the regulators want to help you. They just don't have enough tools, and their structure prevents them from moving fast. You know, right now, just last comment, you guys have seen the interconnection queue reforms that have come through. Anybody has been following that? So they are trying to totally overhaul the interconnection queue. I think it's 10 years too late. And it's always going to be 10 years too late. Every regulation, every ruling, federal government, the IRA, they had what, $77 billion for transmission? That's one project, 2 projects at max. Who cares? You know, money is not an issue. Give me good projects, I'll give you $100 billion tomorrow. Not a problem. Money is the easiest part of this equation. Good projects are not. You know, you have to have good projects that can be built. So that is where I think the solution is going to come from this group presenting it to the regulators, and the regulators, you know, embracing them. And they want to. The staff definitely wants to. They're good people.
But I like this panel, the partnership, like you've heard Jason.
Yeah.
Technology. I'm an electrical engineer. Material science is one of the most difficult engineering, and this guy's a master, right? So his mastery of technology driving the value up, the efficiency down, right? Regulators like to hear that. The
Absolutely.
innovation, not just in technology, but in financing and what utilities bring to bear is pretty powerful that we can kind of get that working. We just worked with Smith Transformers in the Netherlands for 5 years. We have auto transformers, the big stuff that's we've got about 90 of them across the system. The big load autos, load cars. 300 MVA transformer, our standard. We just worked with Smith, redesigned it with the metallurgy and everything to get 420 MVA 24/7. We're already put 5 of them in. 420 MVA. Replace all 90 of them with 420. It's kind of like some of the innovation you're talking about, which, something like a 2X or 1.5X on that, and that can really help us with regulators with that kind of partnership innovation.
Well, I think we are out of time, so thank you very much for
Thanks for listening.
listening to us. Thank you very much for being here.